Hello class, welcome to what is going to be, for now at least, the last section in chapter 13 and the last section of the course reader and textbook that I'm going to cover. At some point in time I might do the last two sections, we'll see. But for right now we're going to talk about tangent lines and derivatives. Super important topic in Calculus 1. It gets revisited again later in Calculus 3 and pretty much every course after Calculus 1. Okay, so it's a super important topic. We can say that Calculus 1 is basically focused on tangent lines and derivatives. This is the main topic of Calculus 1. Okay, everything we do in Calculus 1 kind of revolves around this topic here, right? So recall that the average rate of change of a function from one input to another input is the difference in their outputs divided by the difference in the inputs, right? So we know for a straight line that this is a constant value, right? Because a line has a constant rate of change. For a function that is not constant, that's, a curve, we can find the average rate of change by, this is basically the slope formula, right? The difference in outputs over the difference in inputs. Right. So let's say that we have a parabola, okay, concave down parabola. If I start from a point A and I look at a point B, this line here, the slope of this line is my average rate of change. It's the slope of the line, right? So difference in x values over the difference in y values over the difference in x values. So it's the slope of the line that connects the 2 points. That's what average rate of change is, okay? So what we're going to do is we're going to look at this a little bit differently than normal, okay? I am going to, instead of saying I'm going from A to B, I want to say I go from A to a little bit more than A, right? And I'm going to call the distance between these 2 points h. Right? So instead of I'm going to go from A to B, I'm going to say I'm going to go from A to A plus some value. Right? So that value we're going to call h. So the distance between A and B is h. So I can rewrite this then. Okay. Instead of writing B, I can write it as A plus h. Right? So our equation, f of B minus f of A over B minus A, then turns into f of A plus h. So all I did here was I took this equation and I solved for B. Okay, solving for B gives me h plus A, or A plus h. So when I take this equation, everywhere I see B, I'm going to replace it with A plus h. So f of B turns into f of A plus h. I have minus A. Here, B turns into A plus h. So A plus h minus A is just h. This should look familiar to you. We've talked about this a lot in this course. We call it the difference quotient, right? But now we're talking about its relationship to calculus, right? So what we're doing now is we're talking, instead of about 2 points, B and A, when we have this difference quotient instead, which is, equal to this, we're instead talking about what's happening to A, which is what's important to me. I want A to remain fixed, and I want to talk about what's happening a distance away from H. So everything has to do with H instead of these 2 points, right? So we're just kind of reframing the way that we're looking at things. So instead of calling this B, we're going to call this A plus a value of H, which we know is a distance of H, right? So this is A, this is A plus H. This is A plus H instead of f of B now. Okay. So the line that's connecting these 2 points, A, f of A, okay, and A plus H, and f of A plus H, is called a secant line. A secant line is a line that passes through a curve and connects 2 points, right? It passes through 2 points in a curve. Any 2 points is what a secant line is defined as. So I know we talked about secant as a function. So this is similar. They are related, but now we're talking about the secant line, not the secant ratio. Okay. So it's a line that intersects a curve at 2 points. So what I'm going to do is I'm going to take this secant line, right? So before the slope of this chord, right, that connected these 2 points was my average rate of change. Now I'm going to extend this chord into a line, okay? And the slope of this line represents my average rate of change from this point to this point. And what I want to do is I want to know what happens as A stays fixed, but the distance between it, h, grows smaller. What happens as h goes to 0? Okay. So I'm going to say that P is my point A f of A, and this point Q here is going to be A plus H with an output of f of A plus H. So I'm going to let H get smaller and smaller and smaller, meaning I'm going to bring B closer and closer to A. So the distance between these 2 points is going to get very, very, very close. In fact, I would like to know what happens not at 0, but when I'm infinitely close to 0, right? As close to 0 as I can. So we're going to start with P and Q, distance away of H, and I'm going to bring H to be smaller and smaller and smaller. So this point Q is going to move around my curve, right? It's going to slowly, slowly approach my value of P because the input that goes to it is getting smaller, right? So Q is getting closer and closer to P. Okay. And when H is 0, that means P and Q are the same line. And what happens when they're in the same line is this is no longer a secant line like it was here, right? There's 2 points of intersection. When there's only 1 point of intersection, that is called the tangent line. Okay. So when you have a line that intersects your curve at only 1 point, that is called tangent to the curve. Right? So the slope of my secant line becomes the slope of the tangent line. So again, I'm interested in the rate of change there, right? The slope of the tangent line at x equals a is the limit as x goes to a of f of x minus f of a over x minus a. So remember, this is that point that was changing. A remained fixed. Okay. In all these cases, A stayed still, but the point of Q changed. So its input value was changing. So as a function, we can call that x, and its output was changing as well. Okay. I can rewrite this limit in terms of h. I can rewrite it as f of a plus h minus f of a over h as h goes to 0. That is the slope of this tangent line. So this last form here has a special name, and we call it the derivative of my function at the point x equals a. Okay. This is the fundamental kind of idea of Calculus 1. We have a special notation for derivative, and that notation is f prime of a. There's other notations for derivatives, but for right now, we're still in a pre-calc class. We're just kind of giving you a brief overview of what Calculus 1 is like. So in Calculus 1, obviously, we really flesh out this idea. But the derivative, we generally write as f prime of a. Okay. So f prime of a is the limit as h goes to 0. The distance between the 2 points becomes nothing. And we go from a secant line to a tangent line. And this is how I can write that, the difference quotient. Okay. And so what this is, again, just to reiterate, it's the slope of the tangent line. So instead of average rate of change, it's instantaneous rate of change. It's how my function is changing at exactly this moment in time. So one example that we like to give is think about when you're driving on an on-ramp onto the freeway. You are not going at a steady speed, right? The speed you go when you first get on the on-ramp versus the speed that you are when you're finally on the freeway is completely different, right? So you're changing in speed as you go, so you have a rate of change that's changing over time. So what this point is, the slope of this line, is how are you changing at exactly this point in time? That's a really important idea. So that is related to the slope of the tangent line at this point. Okay. So we call it the instantaneous rate of change. How am I changing? How am I changing in speed or size or what have you at this exact moment, right? Not over this interval, not from this second to the next second, but instantly right now. Okay, so let's do an example. So if my function is 2 over x plus 2, we want to find f prime of 3. Okay, so in order to find f prime of 3, I first have to find this value. Okay, so I'm going to find the limit as h goes to 0. My a in this case is 3. So everywhere I see a, I'm going to replace it with 3. So I'm interested in f of 3 plus h minus f of 3 over h. H does not have a value, right? It's what I'm looking at going to 0. So I'm not going to plug in anything for h. I'm going to plug in a value for a everywhere. And that's going to represent an input into this function and plug that into my actual function and evaluate it everywhere. Okay, so my limit will become f of 3 plus h minus f of 3 over h. Now I want to actually plug this into my equation. So f of 3 plus h, again, if you are fuzzy on how this works, go all the way back to chapter 2 when we talk about plugging in weird stuff into our functions. This is just my input. Everywhere I see x, instead of just writing x, for 3 plus h, that means everywhere I see x, I plug in 3 plus h. So this will be 2 over 3 plus h plus 2 minus, and then here I'm going to plug in 3 everywhere, so 2 over 3 plus 2 over h. So remember, h does not get evaluated. I'm taking the limit of this thing. Now the problem is that as h goes to 0, makes my denominator 0. So I want to simplify this as much as I can algebraically, rather than plugging in a bunch of different values for h and trying to look at this numerically, right? I want to use my algebraic methods. So I can add 3 and 2 together. This becomes 2 over 5. This is a complex fraction, right? So it's a fraction inside of a fraction. So I just want to simplify things. So I can either clear my denominators or I can turn this into a single fraction. It doesn't really matter. So here I'm going to clear the denominators. So I'm going to multiply everything times 5 plus h. And this will turn into 2 times 5. This turns into 2 times 5 plus h. And the denominator turns into that value that I multiply top and bottom by, which is 5 times 5 plus h. Okay. So from here, I'm not necessarily out of the clear because I still have an h here that if I plug in a 0, I'm not yet continuous here, right? So let's finish simplifying this down. I have 10 minus h. This turns into a 25h plus h squared. Okay, so we'll just work this down slowly. So this gets to cancel out. Okay, here I have an h on top and an h on bottom, so I can cancel those. And from here, now I'm continuous at 0. If I plug in 0 here, nothing happens. So I plug in and I evaluate at 0, and I get negative 2 over 25. So the limit of this function as h goes to 0, right? So it's not necessarily this function, but the difference quotient is this. This means that at 3, when x equals 3, this function is changing at a rate of negative 2 over 25. So it's decreasing in value, right? It's a negative slope. So this is the slope of the tangent line at this point. It tells me how I'm changing instantaneously at this point. So at x equals 3, my function is decreasing because the slope is negative, right? Negative rate of change. And this is how much is changing at that exact instant in time. Okay. So at x equals 3, my function is changing at a rate of negative 2 over 25. If I were to draw a line tangent to this curve at x equals 3, this would be the slope of that curve, of that line, I'm sorry. Okay. So a common thing is, now that I have the slope of this tangent line, and the tangent line is so important to me because it has to do with my derivative, what is the equation of that tangent line? Well, I know that this is my function. I know I'm looking at this point on my function, and I know that at this point, this is how that function is changing. It's the slope of the line tangent to it. So remember what we need in order to find a line. I need a slope, which I have, and I need a point. In order to find my point, remember, the tangent line shares only one point in common with my function, and that's the point of interest to me. So if I want to find this line, first I find the slope, which I just did. And then I take my value, in this case x equals 3, and I just plug it into my function, because that point is on my curve and it's on my tangent line. So that is how I find the point on my line, and I've already found the slope. Okay, so we already found the slope. Now we need to find a point, and then I have enough stuff to find that equation. So f of 3 is 2 over 3 plus 2, or 2/5. So I know at 3, my tangent line has an output of 2/5, and at 3, my function also has an output of 2 over 5. And I also know that at 3, the tangent line has a slope of negative 2 over 25. Okay, so using the slope and this shared point of the function and the line, and plugging it into y equals mx plus b, I get the equation y equals mx plus b. I can solve for b. I can multiply the whole equation by 25 to clear this fraction out. I can take my 10 and add 6. So I got 16 is 25. Solving for b gives me 16 over 25. So the slope of my tangent line is negative 2 over 25 x plus 16 over 25. Okay. Here is the graph of my function, 2 over x plus 2. Okay, notice that there is a vertical asymptote at x equals negative 2. I was interested in what's happening at 3. Okay, at 3 I have a 0.25. Okay, and this is also a point on my tangent line. So my tangent line touches this curve only once, right? So notice it's in between this arrow. It never touches it at another time. And it has a slope of negative 2 over 25. So this is the equation of that tangent line. This is the only point in common because it's tangent. And this is how we do that. So that's the relationship between tangent line, slope, derivative, instantaneous rate of change. I know it's a lot, but watch this video once or twice and it'll make more sense a couple of times, right? So let's do one more example. Okay, let's say that f prime of 5 equals 2. So that means that the slope at 5 of my curve f of x here is a rate of change of 2. And at the point 5, my function has an output of 10. So now I have the slope and a point. Okay, I want to find this points a and b. Okay, so b is an x value of 5.2 and a is an x value of 4.6. I have a slope and I have 2 points, so actually 3 points, right? But I don't have the outputs for a and b on the tangent line. That's what I'm trying to find here. Okay, so again, we know a point and the slope of the tangent line, so I can find the equation of the tangent line. So I'll do just what I did before. I know that 5, 10 is a point on the line, and I know that the slope of this tangent line is 2. So I have enough information to plug everything in. So I have y equals m, x is 5, right? 5 and 10 is my point, plus b. So this is also 10, so when I subtract it over, I'll get 0 for b. So that means my tangent line is y equals 2x. Since I know that's the equation of this line, I can plug in the different x values for a and for b, and it'll tell me what the outputs are for a and b. Okay, so if I plug in 4.6, all I have to do is double that, so that turns into 9.2, so that's the point of a. 5.2, I double that because that's the equation of the tangent line, so that turns into 10.4. So this is the point for a, and this is the location for b.